In the world of organic chemistry, there are literally millions of unique molecules. So, how do we even begin to keep them all straight? Well, we do it with a universal language, a code that's designed to describe any structure with perfect crystal clarity. And today, we're going to crack that code. We're talking about IUPAC nomenclature.
All right, take a look at this thing. Seriously, it's just a tangle of lines and letters, right? How could you possibly describe this structure to another scientist, maybe halfway across the world, and have them draw the exact same thing? That's the puzzle we're going to solve.
You see, before we had a system, naming was, well, it was chaos. Names were totally arbitrary. They were based on where you found something, like formic acid, which comes from formica, the Latin word for ant. Or they were just named after people or cool shapes, like Buckminster fullerene. And look, that was fine for a handful of compounds, but it was completely unscalable. Now, contrast that with the IUPAC system. It's like a logical map. The name itself is the blueprint, if you know how to read it. You can draw the exact structure, no guesswork involved. So, how do you bring that kind of order to that much chaos? Well, you don't just make a new list of names. You create a system, a formula, a kind of universal grammar that you can apply to any organic molecule out there, no matter how ridiculously complex it looks. And this is basically the secret decoder ring. It shows that every standard IUPAC name is really built from just two core parts. First, you have to identify the parent chain. That's the main backbone of the molecule. Then you describe all the locants in branches, which are really just the decorations and their exact addresses on that backbone. You put those two pieces together and bam, you have the molecule's unique identity. Now, to use that formula, we're going to need some vocabulary. And this table right here, this is your foundation. It connects the number of carbons in a chain to a specific root name. So 1 carbon is meth, 2 is eth, 3 is prop, and so on. If it's the main chain, the parent, it gets an ane at the end, like methane or propane. But if it's just a branch hanging off the side, we switch that ending to -il. So a methane becomes a methyl branch.
And you might think a system this logical would be super rigid, but it's actually got a pretty cool quirk. For some very specific, very common branch shapes, like the Y shape of an isopropyl group or that cross shape of a tert-butyl group, IUPAC actually lets us use these old-school common names. It's kind of like a little nod to the past, as long as those branches don't have their own branches.
Okay, so we've got the building blocks, we have the formula, and we have the vocabulary. But a language is always more than just words, right? It needs grammar. So let's dive into the core rules that hold this entire system together. Rule number 1 is, without a doubt, the most important. You have to find the parent chain. This is the longest continuous path of carbons you can trace without lifting your finger. And here's the trick that gets a lot of people. It's not always the one that's drawn straight across the page. As you can see in the do box, the true path can bend and turn. The straight path only gives us an 8-carbon chain, but the correct bent path gives us a 9-carbon chain, a no name. So once you've found that parent chain, you've got to number it. Think of these numbers like street addresses for all the branches, and the rule is absolutely crucial. You have to number from the end that gives the branches the lowest possible address numbers. On this numbering scoreboard, starting from the left gives the branches positions 2 and 6, but starting from the right gives them 4 and 8. The rule is simple. You check the first point of difference. Since 2 is lower than 4, the 2-6 path wins. No contest. Next up are the syntax rules, which are actually pretty simple. You use hyphens to separate numbers from words and commas to separate numbers from each other. Easy enough. What's really important, though, is that you list all the branches in alphabetical order. But, and here's the detail that often trips people up, you ignore the counting prefixes like di or tri when you're alphabetizing. So dimethyl doesn't count as a D, it's alphabetized under M for methyl. All right, so those basic rules will handle most cases you'll run into. But, any good system needs a way to resolve ambiguity. What happens when you hit a tie? Well, let's look at the tiebreakers. Okay, here's our first tiebreaker. What if you find 2 different paths that are the exact same length? Which one is the parent chain? The rule is this. The chain with the greater number of side chains becomes the parent. So in this example, one path gives us only 2 branches, but the other path gives us 3. 3 beats 2, so we have our winner. And here's our second big tiebreaker. What if the numbering gives you an identical result from both ends? For instance, maybe the first branch is on carbon 3 no matter which way you count. In that case, the alphabet breaks the tie. You give the lower number to the branch that comes first alphabetically. So here, ethyl comes before methyl. That means ethyl gets position 3 and methyl gets position 6. The correct name is 3-ethyl 6-methyl octane.
Sooner or later, you're going to find branches that have their own little branches, and the system handles this with this really elegant nested logic. What you do is find the longest chain within the branch itself, number it starting from the carbon that's attached to the main parent, and then you put the entire name for that complex branch inside parentheses. It acts kind of like a folder, keeping its own internal numbering, completely separate from the main chain.
The system also works perfectly for molecules that form rings, and the rule for this could not be simpler. You just add the prefix cyclo to the name of the parent alkane. So a 5-carbon ring is cyclopentane, a 6-carbon ring is cyclohexane, and then the numbering rules follow right along, making sure any branches get the lowest possible locants.
So, now we have all the tools in our code-breaking kit. We've got the formula, the vocabulary, the grammar, and even the tiebreakers. So I think it's time for the final test. Let's put it all together and decode a really complex molecule from scratch.
Okay, let's decode this beast, one rule at a time. First, the parent chain. We trace the longest continuous path, and it gives us 10 carbons. So our foundation, our last name, is decane. Next up, numbering. Starting from the right gives our first branches the lowest possible number, landing right on carbon 3. And what's on carbon 3? 2 methyl groups. So that piece is 3,3-dimethyl. Now let's look at carbon 5. We've got one of those complex branches, so we know we're going to need parentheses. Inside that branch, the longest chain is 4 carbons. That's a butyl chain. And it has an ethyl group at its second carbon. So that makes it 2-ethylbutyl. And finally, we assemble the name alphabetically. E in ethylbutyl comes before M in dimethyl. So the full, totally unambiguous name is 5,2-ethylbutyl 3,3-dimethyl decane. See? Every single piece has place.
You know, learning the rules is one thing, but seeing how they can be broken is actually a great way to make sure you really understand them. So let's do a quick code review of some common naming bugs. All right, in case study A, the bug is naming this thing 2,4,7-trimethyl-octane. The diagnostic log tells us it's a lowest locant rule violation. If you number from the other direction, you get the set 2,5,6, which is lower than 2,4,7 at that first point of difference. Now in case B, the branches are at positions 3 and 5 from either end. It's a tie. The bug here is giving the methyl group the lower number. The fix is to use that alphabet tiebreaker. Ethyl gets the lower number, 3, because E comes before M. So the correct name is 3-ethyl 5-methylheptane.
So if you're going to remember anything from all this, remember this codebreaker's cheat sheet. First, always find the longest continuous chain, even if it bends all over the place. Second, number that chain to give all the branches the lowest possible numbers. And third, list those branches in alphabetical order. If you can master these 3, you can name the vast majority of simple alkanes out there. And that, right there, is the real beauty of the IU-PAC system. It's not just some random collection of rules. It's a logical framework that ensures absolute precision. By trusting the syntax, ambiguity is just gone. It guarantees that every single organic structure has exactly one correct name, a universal identifier that can be understood by any chemist anywhere in the world. And that is a truly powerful code.